thing is infinite, so I get infinitely many different blow-ups. They're all derived equivalent, but they're not isomorphic. So let me just make a couple remarks about the fact that most of this is really very classical stuff. So the Cremona action on configurations was studied a long time ago. So some of the people who worked on this are, I think, Cantor, Duval, maybe most of all Coble. This was in the 20s, I think. He was actually the AMS president. Maybe on this list I should put Dolgachev and Ortland. They wrote a book sort of putting some of these classical results into a more modern language. And a lot of this is just for the Cremona action on P2, but Coble, I think, looked in P3, and really there's not such a big difference. And I think this point 3 about the infinite orbit is really a classical fact. This Cremona action is also something that's studied by people in dynamics. So we wanted to know that if you started with a general configuration P, and you kept doing this procedure of make a Cremona transformation at the points and then permute, that you never got back to the same configuration you started with. That was the whole thing we were trying to avoid with this special conditions here. But what would happen if you did get back to what you started with? So if Pn equals P, in the notation that I was using, if Pn is P0, you get a map from a variety back to itself. So from xp0, you do a bunch of flops, and the thing you get back is, in fact, isomorphic to xp0 again. So this is a birational automorphism of the variety. In fact, it's a pseudo-automorphism, meaning that it doesn't contract any divisors in either direction. It's only undefined along curves. And it turns out that if you use 9 points instead of 8, this is a positive entropy pseudo-automorphism. And so it's a dynamically interesting map. Now, I should say that this is only going to work if you choose your P0 very, very carefully. I mean, the fact that all these are distinct is a general condition. Finding P0s that make it so you end up where you started is much harder. It's actually a very high codimension condition, I think. And really, I mean, for this Fourier-Mukai partners thing, we just wanted the general result. But the really interesting problem is to find P that are fixed. So in dimension 2, which is where this was first done, I think from this point of view, McMullen has some ways to find P0. And I think there are various other ways to do the same thing. In higher dimensions, more recently, Peroni and Zhang found some ways to construct P0s that give you pseudo-automorphisms of blowups of Pn. So this Cremona action is not something I made up. I mean, it's both very classical and something that dynamics people study still. But the dynamics case is exactly what we're trying to avoid to get this infinitely many Fourier-Mukai partners. All right, so I guess it's.
But I don't get it. So was it known before that you get infinite?
So at least in dimension 2, it's written up. Dimension 3, I mean, people knew it certainly. I'm not sure it was written down explicitly. I mean, I mean, all the pieces that go into it, I think, are familiar to someone. But not the same people, maybe. All right, are there any other questions?
And what's the situation for kx equals 0
For k?
question?
Well, I think the case that it's a Calabi-Yau threefold is really the main case. This is sort of a generalization of the Kawamoto-Morrison conjecture. Right, it's saying, right, if you have two birational Calabi-Yaus, we know they're connected by flops, and so they're derived equivalent. So this would say there's only finitely many isomorphism classes in a birational class, which is what the Kawamoto-Morrison is about. So I think this conjecture for Calabi-Yau threefolds is probably wide open, and that's the more important case. This thing is actually very close to being a Calabi-Yau threefold somehow. There exists a DLT boundary, so that x delta is a DLT pair with kx plus delta numerically trivial. So it's a DLT log Calabi-Yau, and the Kawamoto-Morrison conjecture should hold for KLT Calabi-Yaus maybe. In dimension 2, we know that from Totaro. But because this is only DLT, it's not a counterexample to that. But I mean, it's sort of close to the Calabi-Yau case. In dimension 2, it's false for DLT. I think this is in Totaro's paper. I mean, it's P2 blown up at 9 general points. All right, so the next example I want to talk about is more or less unrelated, except that it still has the same theme that infinite sequences of flops do weird things. So if there are any other questions about this one, maybe.
So here you have a counted number of okay couplets.
Yeah. Oh, sorry, I should have said.
Is it always most counted one?
Yeah, I forgot to put this on my list at the beginning. So this was proved by Anel and Tohen. The number of FM partners is always at most countable. Sorry, I should have said this at the beginning. Thanks for pointing that out. This is by some kind of Torelli-type theorem for derived categories. So in fact, they didn't just prove a partial result on this conjecture. This is the correct answer in general. OK, well, we can come back to this one if you have questions at the end. But let me start on example 2 now. So this is going to be about asymptotic multiplicities in the relative setting, which maybe you haven't heard of, but I want to convince you this is a reasonable invariant. So the setup is this. I'm going to have a variety x. I'll say smooth projective. I don't really need that. But my example will have this, and I don't want to worry about the hypotheses. I have V, an irreducible subvariety of x. And then I have D, a big divisor on x. Right, so the invariance we're talking about is the following thing. We're going to set sigma v of d to be the limit as m goes to infinity of 1 over m times the multiplicity along v of a general element of md. So you take your divisor d, you take a very, very big multiple of d. You look at, well, what's the multiplicity of a general section along v? And then you divide by m to sort of normalize. And this limit as you take m bigger and bigger exists. So maybe a way to think about this, if d is ample, then sigma v of d is 0. But remember, d might, even if d is ample, it might not be base point free. D could have base locus along some divisor. And so the multiplicity of d itself along v is non-zero. But because d is ample, some large multiple is base point free. And so the multiplicity of this along v is 0, even if for m equals 1, it's not. So this is an invariant that measures the order of vanishing of sections of high tensor powers along a subvariety. And an equivalent way to say this is that sigma v of d is going to be the infimum over all effective divisors d prime that are numerically equivalent to d of the multiplicity along v of d prime. But d prime is allowed to be an R divisor here, or a Q divisor. So if I write it the definition like this, which I'm probably going to do, the way you should think about this, what do you think of d prime being? You think, well, I take a large power of d, I take a general element of md, and then I take d prime to be that thing with coefficient 1 over m. Right? That will be an R divisor that's numerically equivalent to d, but it's going to be relatively less singular along v than d itself was. I mean, I hope this seems like kind of a reasonable invariant to look at, even if you're not into the MMP. We're just saying, OK, I have a numerical class of a divisor. I want to know, among all divisors I could represent that class with, what's the smallest multiplicity I can get? What's sort of the smallest multiplicity of the numerical class along the subvariety? So these were introduced by Nakayama originally. The other paper that works out a lot of their properties is by ELMNP, Ein, Lazarsfeld, Mustatsa, Nakamaya, and Popa. There's also a complex analytic version of these that was by Buxom and came out at more or less the same time as Nakayama's original definition. OK, so sort of the general question I want to address is, how does this invariant sigma v change as you change the divisor d? I mean, if this is going to be a useful invariant, we might hope that it varies well with d. And the answer is it varies very well. So in fact, sigma v is a continuous function on the big cone. Everything I'm saying now was proved by probably all of these people in the papers about it. So what we're saying is just if you have a numerical class, you perturb the class a little bit. You ask, well, what's the multiplicity of this perturbed thing along the subvariety? It doesn't change very much. So the next thing you can try to do is say, well, what if instead of perturbing this where d is big, we take our divisor d and we go towards the pseudoeffective boundary? We're going to let d move closer and closer to divisor classes that are no longer represented by effective divisors at all. And so the big result here by Nakayama, and I think also by Buxom, is that if d is only pseudoeffective, again, pseudoeffective just means you're the numerical limit of big classes, even if you're not effective at all. Then we make the following definition. Sigma v of d of effective, or big. I mean.
Are they the same?
Oh, yeah, sure.
Wait.
I mean, we have this cone. The interior of this cone is the big cone. The closure of the cone is the pseudoeffective cone. The effective classes on the boundary might be effective, might not be effective. The effective cone is some non-closed cone in between these two. But limit of big and limit of effective is the same thing. So here's how we're going to extend this function to pseudoeffective classes, pseudoeffive classes. We're going to fix an ample divisor A and take the limit of sigma v of d plus epsilon A. OK, and now the question burning in your minds is, well, why does this limit exist at all? Right? So if you take a pseudoeffective class, you add a little ample. That pushes you inside the cone. So now you have a big class for any epsilon. Sigma v makes sense there. Now you go back towards the boundary. And the question is, why does this sigma v have a limit? And the good result here is that this is finite. So the limit exists. And why is that? Well, there's a good trick here. So if we took d plus epsilon a for any epsilon, so actually I should say, let's just suppose v is a divisor to make our lives a little simpler, rather than v being some higher codimension thing. If I take d plus epsilon a minus sigma v of d plus epsilon a times v, I get a pseudo-effective class. Because sigma v of d plus epsilon a, this is just how many times does v appear, with what multiplicity is v in the base locus of d plus epsilon a. If you subtract off the number of times the thing is in the base locus, you're still going to get something effective. Or if you have an effective divisor, you subtract off its fixed part, it's still effective. And so the epsilons make it pseudo-effective, but it's not a big deal. That means I can intersect this with the top power of my ample divisor, and I get a positive number. And so this actually gives us an upper bound on sigma v of d plus epsilon a. So it's less than or equal to, I guess, d dot a to the n minus 1, or v dot a to the n minus 1. Yeah, I think that's right. So this limit is finite because we have this cool trick here. Any question about this setup on this asymptotic multiplicity? So far, this is all Nakayama defining sigma v and showing it exists even for pseudo-effective divisors. I promise soon I'll get to the fun example and actually work this out in a case. So what if we try to do this in the relative setting? So you should make the same definition, right? So sigma v of d is going to be the infimum over effective divisors. Sorry, I should say relative setting. I mean, I have a projective family x to s, and I'll call them at pi. So we try to do exactly the same definition as before. So we look over all d prime that are effective and that are equivalent to d over s. So what I mean here is that d dot c is equal to d prime dot c for any c contracted by pi. Is this OK? So I mean, it's just like before, more or less. And you look at the infimum of the multiplicity along v of d prime. So in the case that s is just a point, this is exactly the same thing that we had before. But if s is not a point, this is, I mean, it's a generalization. But again, you look at all divisors, pi numerically equivalent to d, and you take the smallest multiplicity of one of those along v. OK, so this I should have said is for d relatively big, or d effective, say. And you can try the same thing. You can try to extend to the pseudo-effective boundary. So you're going to try to set sigma v of d to be the limit as epsilon goes to 0 of sigma v of d plus epsilon a. Yeah, that's a good question. So that's something to prove, is that if d is big, this is actually a numerical invariant. And so if you, this is, again, checked by Nakayama. I think if you try to do it for classes that are effective but not big, it's no longer a numerical invariant. And so that's why even for effective classes that aren't big, you want to use the limit definition to define it. Yeah, that's a good question. But it's enough to just look at the numerical class. The answer doesn't change. Right, now there's a problem here, which is that this definition, or sorry, this proof that it's finite, sort of relies on the properness of x. We're doing intersection theory on x. There's no way to adapt this proof to the relative setting. And so the example I want to tell you now shows that actually this doesn't have to be finite in the relative setting. It can really happen that you have an example of a divisor where when you try to take this limit, you get an infinite coefficient. So, I mean, Nakayama actually gives a variety of conditions that show that it's finite. Maybe the most interesting of these is that the codimension of pi of v is less than 2, then you get the finite. So for example, if you're working over a point or even over a curve, it's OK. But if the variety v you're measuring multiplicity along lies inside a fiber, for example, and the base is high dimensional, there's no guarantee you're going to get this finiteness. OK, so let me tell you the example that shows this doesn't work. And I promise, even if you don't like these invariants, the example itself is pretty cool. Well, I'll let you be the judge. I shouldn't overpromise. So this is an example that I think was first introduced by Reed and has been studied by Kawamata for some related problems. We're going to look at the versal deformation of an I2 singular fiber. So I'll draw a picture. So our base is going to be two-dimensional. Above the central fiber in the base, we're going to have an I2 fiber, so two rational curves meeting transversely at 2 points. Now there's two divisors in S, the x and y axes, let's say. If you move over one of these things, you smooth one of the nodes. So the general fiber over the x-axis is going to be a cubic with one node. Over the y-axis, you smooth the other node. And then everywhere else, you get a smooth elliptic curve. So let me call these two curves in the central fiber C1 and C2. So here's what happens here. This curve C1 is a rational curve with normal bundle -1, -1. And you can flop this curve. And it turns out that after you flop the curve, the new thing you get is isomorphic to what you started with. And C2, similarly, is a rational curve with normal bundle -1, -1. So you can flop C2. Again, flop C1, I just mean you blow up this rational curve, you get a P1 times P1, and you blow down the other ruin. So you can flop C1, then you flop C2, then you can flop C1 again, and you get an infinite sequence of flops like this, where you keep flopping the same two curves again and again. Now here's what to think about. Say I started with an ample divisor on my x. So it's going to have no multiplicity along C1 or C2. I flop C1, and I take the strict transform of the ample divisor. Well, it's not going to be ample anymore. It's going to now have a base locus along C1, the curve I just flopped. If I then flop C2 and take the strict transform, I'm going to get another divisor, this time with base locus on C1 and C2. If you flop C1 again, you take the strict transform, it's going to get even more singular along C1. And every time you flop one of these curves, the strict transform of your divisor is going to get more and more multiplicity along those two central curves. And so when you take the strict transform and there's some very, very long sequence of flops, you sort of expect you should get something that's extremely, extremely singular along those curves. And if you calculate it, that's exactly what happens. So let me start with an ample divisor H0. And I'm just going to make a table of the multiplicities of the strict transforms. All right, so I'm going to have 4 columns in my table. The first column is just what's my divisor dot C1. Second is what's my divisor dot C2. Third is what's the multiplicity along C1. The multiplicity along C2. So I'm going to start with an ample divisor. We might as well assume it's 1 on C1, 1 on C2. No multiplicity along either one. So now you can take the strict transform this under the flop of C1. And I'm going to call that divisor H1. And let me actually sort of secretly swap the two curves so that each time I'm always going to flop the first of the two curves. Right? So here's what you get. If you take the strict transform of your ample under the flop of C1, it gets multiplicity along one of the curves. It increases its intersection with the other, and it becomes negative on the curve that you just flopped. So you could do the same thing again. I mean, it's pretty easy to make these calculations, but I'll spare you. You get something with higher multiplicity with, higher intersection with C1 and with C2. And again, the multiplicities grow like I promised. Let me build the suspense here for another line. It's 7 minus 5, and these start to increase. And if you actually write down the formula, what you find is that Hn is going to have intersection 2n plus 1 with one of the curves, negative 2n minus 1 with the other. So those are growing linearly, but the multiplicities along these two curves are going to grow quadratically. And in fact, you can see these are sort of converging to some numerical class. If I rescale this by a factor of 2n, they're going to converge to some pseudo-effective class D. Right? This D is numerically the limit of effective classes, so it's pseudo-effective. By 1 minus 1, I mean D is the class that's 1 on C1 and negative 1 on C2. And in fact, more precisely, what's true, 1 over 2n Hn is pi numerically equivalent to D plus 1 over 2n H0. Did I get this right? I think so. Now what do we have on the right-hand side here? We have a pseudo-effective divisor plus a sequence of ample divisors going to 0. And this is exactly what we needed to compute the asymptotic multiplicity invariant. This is what you need for the limit. Right, so here's the final reveal. What's sigma C1 of D going to be? Well, this is the limit as n goes to infinity of sigma C1 of D plus 1 over 2n H0. This is the limit as n goes to infinity of 1 over 2n times the multiplicity of Hn along along C1. So this is the limit as n goes to infinity of 1 over 2n times n minus 1 times n over 2. And this is quadratic, this is linear, and this limit doesn't exist, it's infinite. So let me just say again in words what's happening here. We have this pseudo-effective divisor class D. It's the limit of these effective classes Hn. The thing is, if you take a sequence of divisors Hn, 1 over 2n Hn, getting closer and closer to D, the multiplicities of these Hns along the curve C1 are not converging to any limit. The closer and closer your effective class gets to D, just the bigger and bigger and bigger this multiplicity gets. And in this sense of Nakayama, this asymptotic multiplicity is actually infinity in this example. The finiteness was not in the relative setting, and the proof of the finiteness used sort of the properness of X to do this intersection theory trick. And without that, you can't run that argument, so there's no proof of finiteness. And in fact, yeah, finiteness doesn't work. So let me just take one more minute to one final slide here, which is the question probably on everyone's mind, which is, who cares? So these invariants actually show up in the MMP quite a lot. And so here's a typical way that you use these. If you're given a pseudo-effective D, you set n of D to be the sum over all gamma divisor of sigma gamma of D times gamma. So this is an effective divisor. Then you set P of D to be D minus n of D. so this gives us a decomposition. Our divisor D is the sum of this divisor n of D and the divisor P of D. And in fact, if X is just a smooth surface, this is a decomposition that you've seen before. If n is a surface, this is nothing other than the just standard Zariski decomposition of a divisor on a surface. So in higher dimensions, you can use the same definition. Different people call it different things, but this D equals n sigma of D plus P sigma of D is the usual notation. It's called the divisorial Zariski decomposition. I think that's Buxom's name. Or the Nakayama Zariski decomposition. I mean, it's the same thing, just different words. The sigma decomposition is what Nakayama calls it. So the upshot of this thing with this infinite example is that if you want to use Zariski decomposition in the relative setting, you need to be a little careful, because this is not going to work if you have a coefficient that's infinity. Then n of D is not a divisor, and P of D doesn't make sense at all. And that's the conclusion of the second example. I mean, doing Zariski decomposition in the relative setting is something that people do actually want to use. This is not some totally esoteric thing. And again, this example just shows that this n sigma is not necessarily defined, because it might have some coefficient that's infinite. OK, I guess I will stop there.